Hello everybody, and welcome to lesson 1.4, graphing polynomial functions. So before we start today, we're going to talk a little bit about some terminology. First, we're going to talk about the degree of a polynomial, and that is the greatest exponent on the variable on any term in the polynomial. So for example, if I wrote out this function, let's say y equals 3x squared plus 2x cubed minus, let's say 6x. I know that this function is of degree 3 because the highest exponent is 3. Even when you have functions that aren't quite as obvious, let's say in factored form, x minus 2, x plus 1, x minus 7. Again, I know that the degree here is also 3 because if I went ahead and I did the expansion, eventually I'd end up with an x cubed term. The roots of a function, they represent the x-intercepts. So basically wherever your function crosses the x-axis. Okay, so let's move on to some familiar functions, and we'll talk about their degree. Now, a linear function is usually, or is always, in the form of y equals mx plus b. I know that the degree of this function is 1, because the highest exponent on x, even though we can't see it, is a 1. The maximum number of roots that this function can have, so the maximum number of times that this function can cross the x-axis, is 1. However, it's a little stipulation to that. If you had a horizontal line that goes through the x-axis, then you would have an infinite number of roots. The minimum number of roots that this function can have is 0, because what we could have, essentially, is a horizontal line that just doesn't go through the x-axis. So for example, if I drew a horizontal line through the x-axis, well, that horizontal line touches the x-axis infinite number of times, so therefore we get infinite roots. A horizontal line not through the x-axis, so basically anywhere else. So if I took this line and I moved it anywhere else, then it never ever touches the x-axis, so this one would have 0 roots. Okay, so let's move on to quadratics. Now, in previous math classes, you would see quadratics in these 3 forms. Standard form, y equals ax squared plus bx plus c. Remember that the c does end up being your y-intercept. You would see it in factored form where you have your stretch factor on the outside, x minus s and x minus t, where s and t are the roots, and vertex form, which you probably won't see too much in this course, but it's a good idea just to recall it, ax minus h squared plus k, where h and k is the vertex of the parabola. Now, in each one of these cases, the degree is 2. Clearly, in standard form, you can see that the highest exponent is 2. Again, as I explained on the previous page, where if you have something in factored form, the number of roots gives you the degree. So we see x twice, so I know that this is degree 2. And again, in vertex form, the exponent here is 2. So, if we take a look at the graphs on the right, we have the parabola in blue. Number of possible roots that will have, well, 0, because the vertex is above the x-axis and it opens up. In red, we have the vertex that lies exactly on the x-axis, so that is the one and only point that lies on the x-axis, so we only have 1 root there. And then finally we have the green parabola, where we have 2 very distinct roots. So now I want to take a look at a cubic function. Now normally I would handle some graphing calculators and we would do an investigation, but because we're doing video lessons, I'm going to show you a whole bunch of cubic graphs, and what I would like for you to do is I want you to keep in mind where the x-intercepts are, where the y-intercept is, and the end behavior of each function. So here are the cubic graphs. Okay, pay attention to the equation and pay attention to where the x-intercepts are, where the y-intercept is, and where how the end behavior acts. Okay, so now that you've seen all of these graphs, let's make a few conclusions about each one of them. So first we're going to talk about the number of roots a cubic function can potentially have. A cubic function, as you saw in the previous graphs, can have 1, 2, or 3 real roots. It can never have 0 roots. And that's just because of the end behavior of the graph. As you noticed, one end of the function diverges to positive infinity, while the other end diverges to negative infinity. So one end rises while the other end falls. And so because of that, you must cross the x-axis. Now, we're going to talk about turning points. So I'm just going to go back to our graphs. Now, what a turning point is when your function changes direction. So for example, in example 8, let's say, if we start at the very leftmost point of the graph, which is right here, the function is decreasing. So decreasing, 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 until we get to this point here, which is our turning point. Once we hit the turning point, our graph changes from decreasing to increasing. So here's a turning point. And if we keep going, increasing, 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 we get to this point, and again, we hit another turning point where our function changes directions, and we start to decrease again. So turning points are where your function changes directions. Now, in a cubic graph, the maximum number of turning points you could potentially have is 2. As a general rule, the number of turning points you can have is always 1 less than the degree of your function. Okay, so now we'll talk about the end behavior of the graph. So we already talked about how one end diverges towards positive infinity and the other end diverges towards negative infinity. How that's determined is by looking at the sign of the leading coefficient. So again, let's go back to our examples. 7 and 8 are perfect examples. Our leading coefficient here is positive. So in a cubic graph, we will rise to the right and we will fall to the left. When our leading coefficient in a cubic graph is negative, the end behavior changes. So a negative leading coefficient means you are going to fall to the right and rise to the left, which is conclusion number 4. So the last thing we're going to talk about is the multiplicity of the roots. The multiplicity determines the shape of the graph. If you have 2 equal roots, or a root that is raised to the power of 2, we say it's multiplicity 2. That particular root will give us a turning point. So for example, the graph on the left has a turning point at the root x equals positive 2. And we know that because of the exponent. If a root has multiplicity 3, or 3 equal roots, then we have something called a point of inflection. In this particular graph on the right, at the root x equals 2, I know we are going to have a point of inflection, and that's given by this exponent here. So what we're going to do now is we're going to graph a function, keeping in mind all of those rules. So, 3 things that you need to sketch a function. First, you need to list your x-intercepts. Remember, an x-intercept happens when y equals 0. So basically what we're going to do is we're going to take each one of these brackets, set it equal to 0, and solve for x. So I know that I have roots at 4, 2, and negative 3. The way I remember this is brackets lie. Anything inside the bracket, you're always going to use the opposite sign. Okay, so let's plot those points. 1, 2, 3, 4, 2, and negative 3. The next thing we want to plot is the y-intercept. And that happens when x equals 0. So let's solve for that. If I sub in 0, we have 0 minus 4, 0 minus 2, and then 0 plus 3. When we simplify, we really end up with a negative 4 times a negative 2 times positive 3, telling us our y-intercept is at 24. And because this is a sketch, as long as you label everything, that would be fine. And the final thing is the end behavior of the graph. First, you have to determine what kind of graph this is. So we'll go back up to the question. I have a maximum 3 roots. That tells me that my function is of degree 3. So I know that this is a cubic function. And in a cubic function, if the leading coefficient is positive, we rise to the right and we fall to the left. If the leading coefficient is negative, we do the opposite. Here, our leading coefficient is positive 1, so we will rise to the right and fall to the left. And once you've determined all of this, then it's just a matter of connecting the dots. So I know that we are going to rise to the right and we are going to fall to the left. And then connect the dots. So I know I'm going to have a y-intercept here that eventually will connect down to this root. And there we go. And because we're doing a sketch, where this curve happens is not entirely important right now. If you really want to know where it is, you could probably sub in a value, let's say x equals 3, and into your formula up here, and see what y value you get. But for now, all I'm concerned about is x-intercepts, y-intercepts, and the end behavior. Okay, so let's move on to Quartic functions. Again, I'm going to show you a few graphs, and you're going to come up with some conclusions. Same idea as last time. I want you to take a look at your function. I want you to see if you can determine where the x-intercepts are, the y-intercept is, and what the end behavior would look like. So now that you've taken a look at those, we're going to come up with the same kinds of conclusions that we did for a cubic function. So the first thing we're going to talk about is the maximum number of roots. If this is of degree 4, then the maximum number of roots we can have is 4. And because of the end behavior, we can actually, in fact, have 0 roots. Because if you notice, in all of our graphs, the end behavior, both ends either rose towards positive infinity or they fell towards negative infinity, as in example 5 and 6. So 0 is a possibility for a quartic function. Since this is of degree 4, I know that we can have a maximum of 3 turning points. Remember, the number of turning points, or the maximum number of turning points, is always 1 less than the maximum number of real roots. I already mentioned what the end behavior for a quartic looks like. Both ends end up doing the same thing. They either both rise towards positive infinity or both fall towards negative infinity. And this happens, again, based on what the leading coefficient is. If we go back to our graph, or graphs, for example, example 3, we have a positive leading coefficient, so both ends rise. In example 4, we have a negative leading coefficient, so both ends fall. And finally, we talk about the multiplicity, which follow the same roots as a cubic function. Multiplicity 2 tells us that we have a turning point, and the triple root, multiplicity 3, tells us that we have a point of inflection. So again, keeping all of that in mind, let's try and graph a quartic function. Same rules as last time. List your x-intercepts. So brackets lie, meaning we have a positive 4, positive 2, negative 1, and negative 3. So we'll plot those first. Negative 1, negative 3, 2, and 4. Your y-intercept, that happens when x equals 0. So if I sub 0 into the first bracket, I would have a negative 4, then a negative 2, positive 1, and a positive 3. Again, giving me a y-intercept of 24. And now we have to determine the end behavior. So to determine that, I have to distinguish what kind of function this is. I know it's a quartic function. And when we have quartic functions, both ends will end up doing the same thing. In this case, because our leading coefficient is positive, both ends will rise. Once you've listed all of those things, you're just going to connect the dots. So I know that both ends rise, so my first and last root, I know that lines will come out of it and go towards positive infinity, and then it's just connecting the dots. So I'll connect the 3 and the negative 1. I'll try my best here on my tablet. And there we go. If I asked you to predict the shape of a quintic function, well, we'd follow the same rules. Start with your x-intercepts. X equals positive 4, positive 2, negative 1, negative 3, and negative 5. And we can plot those right away. And we will determine our y-intercept. So 0 take away 4, 0 take away 2, 0 plus 1, 0 plus 3, and 0 plus 5, giving us a y-intercept of 120. And again, because it's a sketch, just label everything the best you can. Now finally, the end behavior. Again, determine what kind of function this is. I have 5 roots, so must be a quintic. Now, quintics, like cubics and any odd degree function, will follow the same rule. A positive leading coefficient will mean you will rise to the right and fall to the left. A negative leading coefficient means you will rise to the left and fall to the right. So in this case, we will rise to the right and fall left. And just as an aside, all even degree function follow the same rules as the quartic function we just did. Both ends will rise if you have a positive leading coefficient, and both ends will fall if you have a negative leading coefficient. So in this case, again, we rise right and we fall left, and now it's just a matter of connecting the dots. And there we go. So that's it for the lesson today. If you have any questions, please make sure you write them down, and I will see you in class. Take care, guys. Bye.